This is going to be a review of thermodynamics. So what is thermo? Thermodynamics. Just think of it as heat plus flow, okay? Or any forms of energy or other form energy. Messed up there. Okay, like work or electricity, and then flow, like the direction in which it's going. So, main takeaway of thermo systems, like simpler states. You understand this, you understand thermo. It's a little bit more complex than that, but you get the picture. So you have open, this is some vocabulary based with open versus closed, but it's still important. Open versus closed versus isolated systems. So what are these? These are systems that are exposed to heat escaping or entering them. Closed, that won't happen. Open, that can happen. Isolated, neither heat nor work can that happen. So stable versus metastable versus unstable systems. What are these? Stable, it's where it has the least amount of Gibbs energy, has a little bit more Gibbs. This one has the most. Gibbs energy, what is Gibbs energy? G is equal to H minus T or S. We'll get to that more later. Basically, just your amount of free energy dictates how stable your system is, or how much in equilibrium it is. I'll give you an example. In material science, you have graphite and graphite, which is a metastable, and then you have finally diamond, which is a stable form, which are both forms of carbon. Okay, and it'll look something like this. You have your Gibbs free energy right here, and then you'll have your slopes going like that. As you can see here, you'll see your diamond. Actually, you'll see your graphite right here, graphite. Then you'll see your diamond right there. Okay. And again, this is just a mostly a review for my sake, so I don't forget this shit. Or this stuff. I'm sorry. But hey, if it helps other people, then it helps other people. I'm glad to help, always. And so then you have isothermal versus adiabatic. Well, I don't want to overwhelm y'all, but mainly these are the two terms you have to remember. Of course, there's also like, what's that term called? Isochoric systems. These just describe what constants you have in the systems. This is constant pressure, and temperature can change. Well, this is constant temperature. Constant temperature. Okay. God, this looks so bad. I'm just doing this really quickly. I hope that later videos can be a little bit more neat. But now I want to get to the heart of the matter, which is spontaneous. Actually, there are a little bit more terms I'll cover. You have your extensive, and then we'll get to the heart of the matter. Extensive versus intensive variables, and you have state versus process variables. Process variables. Now, what do these mean? The state is something that relies on the state of something to change. So you have your state and process variables. Your state is examples like entropy and entropy, process, heat, and work. So state is basically quantity which can be determined, like the state of the system at a single moment in time. They rely on just the current state, while the process requires, like the interval between those two states. Okay, and then you have your extensive and intensive variables. Intensive relies on, or better yet, extensive relies on quantity. Relies on quantity. Intensive does not. So when I say relies on quantity, it relies on like the bulk matter of the system, like mass and density, right, or volume. these are not density, just mass and volume. How much you have in the system is going to determine its extensive property, which is intensive like temperature. And that temperature doesn't really rely on how much you have in the system. Temperature is just in and of itself just based on heat. So now to get to the heart of the matter, spontaneous versus driven process. Now spontaneous will occur on its own. Driven requires some external agent. And because of this, since it occurs naturally on its own, it doesn't need a push. You assume that it's going to occur faster, right? And because of this, it's going to be irreversible. So since this one requires an external agent, it's going to, take a little bit longer than the other one. So I would call this one reversible, since it doesn't have enough of a force to get going as the other one. That's the way I think of it, at least. Now, when you think about reversibility, you start to bring in the word equilibrium into the equation, as we mentioned earlier. Equilibrium. I know this looks really bad. I'm actually filming. Let me turn this. Crap. I'm actually filming from my phone, and I'm writing while looking at my phone screen, so just bear with me. Equilibrium is how stable a system is, right? And it's based on G, but also H minus TS, and your TS is going to be based on the second law of your system, or of the thermodynamics. Second law of thermo. We'll get to all the three laws. Second law of thermo, which means that the entropy of the universe is always increasing. Then the third law says that at 0 Kelvin, entropy is 0. Although in reality, it's impossible to achieve exactly 0 Kelvin. Some people have been really close to it, but 0 Kelvin, pretty much everything would freeze. That's why it's really hard. You're always going to have at least one little atom moving. And so when you get to equilibrium, you start to ask yourself, if a system's irreversible, what does it have to do with equilibrium? Well, we know it's spontaneous, right? So now we can determine it's irreversible. And you'll get questions like, okay, so what would happen in an irreversible system or in a spontaneous system? Determine the entropy of the universe. What's most likely going to happen with the entropy? And that's where you'll say that it's most likely the entropy is going to be increasing. So it's going to be positive because you want your G to be negative, right? You want a high equilibrium for a spontaneous system. Lower free energy, lower G, synonymous with higher equilibrium. And that's synonymous with higher entropy. Now you're thinking in equilibrium, I thought the entropy was always, was going to decrease because entropy means disorder. Sort of. You have your entropy of universe, you have your entropy of your system, plus your entropy of your surroundings. Now the entropy in the system might very well be decreasing, but your entropy in your surroundings will increase. Heat might be escaping the system, but it will go into the surroundings, and overall your entropy of your universe will increase. And so this will stay consistent with this. Now for the driven process, which is the opposite of the spontaneous process. You have your DS, reversible system, plus your DS of your surroundings, or triangle, right? Same thing. It's going to be 0. Okay? 0, which means no change in entropy occurs, which is why you're able to reverse it, because when something occurs. So it does sound weird because you're asking, wait, but it is 0, so what are we reversing? You're reversing, this is 0, you're reversing heat. So you have like two bodies, right? One's hot, one's cold. The heat goes this way. You couldn't do that by just raising the temperature here. So then this becomes hotter than this one. And then the heat will go back. Thus you reverse it. And it's consistent with the second law, because the second law says your entropy will always increase. Well, here we have no entropy because there's no change, or I'm sorry, there's no change in entropy. Okay, increase in entropy. Now, this is just, these are just my main takeaways, just how I think of it. Again, if I miss some stuff, just feel free to let me know. Freezing of water, yes, dq. ds dq over T, that's what your entropy is going to equal. It's heat over temperature. So if you freeze water, 0. If you freeze water, that's another example. There's no heat. That goes to 0. Thus, you have another reversible process. Freezing of water. Another example of a reversible process. And that part is tricky for me. Like, a reversible process, what? ds over 0. Actually, they're both tricky subjects. Increase entropy, systems of surrounding. Let me cover the laws and then I'll finish this. The first law, we already went over the second law. First law, your energy over Q plus W. So internal energy plus heat plus work equals heat plus work. So du, another way to write it, dq minus p dB. Because work, as we know from gas laws, PV, okay? Energy can be converted from one form to another. Bro, this lighting is horrible. Is that better? But not created or destroyed. Okay? That's your first law. We already went over the second law. And then your third law, we already went over that too, actually. And then you have a zero law. Zero law. And this one just says if you have two different processes or two different systems in equilibrium, with a third system, they're in equilibrium with each other. Dude, why do I keep writing? It's like your A equals B, A and B equals C, then A equals B, right? And yeah, I'll elaborate more on all of this, and I'll definitely try to make these more better as we go.